Hello, my name is Martin Martinez, and this is Lab 4 Circuits and Capacitors. This is a presentation for Physics 2112. To begin, we'll kind of go over some of the key principles and equations used throughout the experiment and the lab. First is Ohm's law, which is delta V is equal to IR, I being current, R being resistance, and V being voltage. Circuit rules that, like for a loop, the total voltage or the total delta voltage is equal to zero, and also the node rule, which is the current in is equal to the current out. We'll also be using quasi-steady states just to keep all of this like actual. Um, uh, we'll also use kind of some of the basic capacitor rules and equations. For potential difference, delta V of the capacitor is equal to Qs over E naught A, and capacitance, which is going to be C equals Q over delta V of the capacitor. That's what that subscript C means, which is also equal to E naught A over S. We'll also be talking or kind of considering energy and charge conservation, uh, the resistor capacitor circuits over time, and also this linearization that will be coming in handy towards the second part of the experiment. But that's going to be the equation that we use to relate delta V over V naught and RC over time as well. We'll go ahead and start with part A of the experiment, and this is the charges and energy conservation in a series circuit. We just kind of mocked this circuit up in the software and read the current at both I1 and I2 as seen, the ammeter at the top and the ammeter at the bottom. Um, and we saw that they both read 0.02 amps, and that's what was read from the amp meter. And it's same if you even did it backwards, even though just one's conventional current and one's the actual current of the electrons, but it should be the same, and it read the same. And then when we switched out the amp meters for voltmeters, we got a current of 0.02 and a delta voltage of 3 volts. And since the closed circuit should equal zero, we're going to go ahead and check this, but delta V at the battery is 3 volts, like a 3-volt battery. Delta V at the 47 ohm resistor, which is the first one in that series there, was negative 0.5, negative 0.959 volts. And then delta V at the 100 ohm resistor was negative 2.04 volt. 1 volts, and as expected, the sum of this should be zero, and it is zero. Just to kind of give a visual, this is the voltage change over time. As you can see, it's initially zero, then the battery brings it up to that 3 volts. It continues in the wire. In the entirety of this experiment, we're assuming that the wire has no resistance. So when we get to this first resistor of 47 ohms, it drops negative 0.959 volts. And then again remains constant from D to E, and then E it experiences that 100 ohm resistor, and then it drops the negative 2.041 volts. And as expected, those two added together bring it back to zero, and then the loop continues again from that left side. We'll go ahead and answer some of the additional questions that were posed. Why doesn't the addition of the voltmeter change the ammeter reading? The high resistance of the voltmeter prevents a large amount of current from flowing through it, leading it to have little to no effect on the current in the rest of the circuit. What happens if the ammeter is connected in parallel with a 100 ohm resistor? Well, I ran this, and it's both amp readers read 0.06 amps. And then some resistance in different elements of it. The 47 ohm resistor, if we take the voltage running through it, the 0.959 divided by the amps, we get 47 as expected. The 100 ohm resistor, we'll take the 2.041 volts running, and we'll divide that by the 2.02 amps running through it, and that gives us 100 ohms as expected. The resistance of the wire, it's zero because we're treating it as such, and that will show us that there's 0 volts running through it with 0.02 amps, and same thing with the amp meter. And on to part B of the experiment, we'll look at a resistor capacitor circuit. What happens to the bulb when the battery is connected in series to this RC current or circuit? The bulb shines very brightly to begin with and then slowly dims off. What happens to the bulb when it is connected in series to a charged capacitor? It's the same result as above. And then what happens to the current in the circuit in both scenarios? It starts off high and slowly decreases till zero. For the time taken for a capacitor to charge/discharge with bulbs of varying resistance, for the 10 ohm bulb, it took about 9.4 seconds to both charge and discharge. Those times are very similar, and that's kind of the average of the both. For the 20 ohm bulb, it took about 18.1 seconds. Now on to more of the data heavy side of the experiment. These are some of the results that I gathered. The T is time in seconds, and the V is voltage, and this is the potential difference versus time of a dissipated or discharging capacitor. Um, and we'll go ahead and look at more of this. This is just a graph, as you can see. It's kind of like a downward slope, but we're going to go ahead and graph it in a different sense in the next slide, and kind of be able to break down a little bit more of what that means. If we go ahead and use the equation from the first slide, we can go ahead and graph natural log of delta V over delta V naught. Delta V naught just being that initial voltage that we read. We can go ahead and graph that against time, and that gives us more of like a linear, more like a nicer looking graph. And then we can go ahead and put a linear best fit on that, and we get a slope of negative 0.1666. With that, again, that first equation, we can equate RC is equal to negative 1 over slope. And we can go ahead and solve that. And that gives us an RC of 6. And we can go ahead and check that against our actual results, which is an R of 30 and our capacitance of 0.2 farads. And that go ahead and gives us a value of 6 as well, which kind of validates what we have, what validates our experiment. We'll go ahead and wrap up with the what if statements. What if you were doing this lab in real life, use an actual ammeter instead of an ideal simulated one? What's the difference about the real ammeter, and how would it affect the circuits you hooked it up to? Well, ammeters are designed to have very low resistance, ideally none. In truth, all objects have some sort of resistance. So if we were to run this experiment in real life, we would see a slightly lower current than expected because when in series because of the addition of the resistance of the ammeter. What if you're doing this lab in real life and used a real battery to charge the real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? Explain. So our model assumes that the resistance in the wire and battery are negligible, allowing the capacitor to flow instantly. That would be the case if we were to simulate this in our software. It would instantly charge. But in reality, both the wire and battery have resistance. So if we were to do this in real life, the capacitor would take some time to charge. It would not be a huge amount of time. It would be pretty small, but it would not be instantaneous as simulated.